So let's hear now about scalable temporal motif dense subnetwork discovery with Ilie.
Can I start?
Yeah, go ahead.
So thanks for the to the organizers for inviting me, and I'm sorry for not attending in person. Today I'm going to present this joint work with Fabio Vandin and Aristides Gionis. Okay, so as many of other people did, let me start by defining the notion of temporal networks. And in particular, in this work, we consider temporal networks as a fixed set of vertices, which represent the entities of the system, and a set of directed edges, which represent the relationships among the entities of the system. So edges are triplets of the form of a static directed edge and the time in which this edge occurs. So again, this can be friendships over a network, or like hyperlinks among web page, or many other things. And we call the pair GVE a temporal network. So one important thing is that we think about temporal networks as originating from systems that produce a lot of data. So for example, let's say message networks or social networks, where we have a lot of interactions over time. So the system is highly dynamic. Now, let me make a step back and introduce static subgraphs. I'm not going to spend so much on it, but we think of subgraphs, motifs, or patterns as small structures. So these are usually defined by classes of non-isomorphic subgraphs that capture important properties of the underlying graph. So by looking, for example, at the count of these patterns, we can really understand and identify important properties about our underlying data. There are many applications of static subgraphs. So for example, in biology, they can capture important relationships between genes. In social network analysis, we can study, for example, triadic closure and many other different problems. So what about temporal networks? Well, for temporal networks, as we saw today out of times, we try to extend the definition of static subgraph to the temporal domain. So while there are many different such definitions, they all share, let's say, a common ground, in the sense that they are made of two important things, which is, first, they are defined through a static subgraph, which, again, in analogy with the previous case, is some sort of shape, a small, let's say, subgraph, a small shape, that captures an important property of the data that we have, and a temporal ordering, where the temporal ordering captures how the information flows over the structure that we have already defined. So we have a static structure, and then we look at how information flows over the structure. So here, we saw today many times, we see on the left a temporal path where information can flow over this path, since the first interaction occurs before the second one in time, while instead this is not true for the second case. Sometimes for temporal motifs, we may have also additional information. So for example, we may have labels over nodes or over edges, and we can try to use this information to define, let's say, in some sense, more meaningful patterns on our networks. But this is not mostly the case for this talk, so I'm not going to go into details for this particular thing. Now, being a little bit more formal, the definition of temporal motifs that I'm going to adopt is the following. I define a temporal motif as a pair, M, which is K and sigma, where K is going to be a directed and weakly connected multigraph with K nodes and L edges. So the important thing is that this is a multigraph. And so, for example, we have two examples here. K1, where we have no, let's say, parallel edges, when instead with K2, we have two parallel edges in this case. So K nodes and L edges. Good. Now we need to define sigma. Sigma is going to be an ordering of the K edges of the multigraph K. So intuitively, sigma is going to represent the temporal dynamics that we want to capture with our patterns. So, for example, if we fix K to K1, which is this subgraph in figure A, then we can define sigma in two different ways. So, for example, we can define sigma on the left, sigma L, that forces the first, let's say, edge to occur before the second one, while instead sigma R is the opposite. So again, in analogy with the example that we had before, sigma L is time respecting, while sigma R is not. Now, we defined the notion of temporal motif, but we're going to have some data. So we now define the notion of temporal motif occurrence. And the temporal motif occurrence is going to be for a given graph and a value of a parameter, which is delta, that is going to be clear soon. As a time-ordered sequence, and this is very important, the sequence is S is time-ordered, of L unique edges from the temporal graph, such that there exists a bijection from the vertices appearing in the sequence to the vertices of the motif. So note here that I'm representing the motif as the sequence sigma. So in the previous example, you can see that you can represent the motif as just like simply its sequence ordered according to sigma, where the sequence is of edges of K, of course. So basically what I'm saying is that there should be a bijection that respects the ordering of the motif and therefore maps the sequence S on the motif. And all the sequence occurs within the delta time. So what this means is that the sequence has bounded duration, and this duration is bounded by delta. Fine. So I need to add two additional definitions, then we're going to see an example of an occurrence of a motif. In particular, we define the count of a temporal motif as the number of delta instances of a motif in a given graph. And then we define S of W as the set of motif delta instances or occurrences among the vertices in W. So what this means is that I look at the vertices in W, and I look at all the motif delta instances among them, and this is the set of SW. Okay, great. Just to fix some ideas, let's look at an example. So I define a temporal graph and a temporal motif. Here I'm using Ti just to say sigma I. So if I want to look at instances of this particular temporal motif in the graph, well, the only edges that can possibly form a motif like delta instances of this motif are the one which are zigzagged here. But of course, remember that I need to define also the value of delta. So suppose that I fix delta equal 10, then of course I'm going to have 4 different sequences of edges that are possible candidates, let's say, to be delta instances of the motif. But over these 4 possible sequences, I'm going to have only this sequence in C, which is going to be a delta instance because it can be mapped on the motif, respecting the ordering of the edges, and occurring within delta time. So for example, sequence B can be also mapped following the ordering, but exceeds the time of delta equal 10. And instead, the other sequences cannot be mapped by just like following the ordering of the motif. Okay, great. So why do we care about temporal motifs? Because one of the problems that has been studied a lot in literature is the following. I'm given a temporal graph, a temporal motif, and a parameter delta, and I want to obtain the count of the temporal motif. So the decision version of this problem is unfortunately NP-hard, as you may know just by probably thinking of a reduction from some clique problem, K-clique. But the interesting part, as we already saw today in some talks, is that this problem is NP-hard even for shapes for which, like in the static case, there are polynomial time algorithms to count all their occurrences. So for example, for star-shaped graphs, you can count star-shaped graphs in polynomial time on undirected or directed graphs in static case, but you can do it in the temporal scenario. So we immediately start to realize that scalability and efficiency are going to be key challenges for any algorithm that wants to deal with temporal motifs on temporal networks. Okay, great. So this is for the theoretical part, but temporal motifs are also interesting to study for their wide applicability. So in particular, there are many different applications that you can think about temporal motifs. So just to name a few, they enable, for example, realistic stochastic block models where you can enforce like transitions according to the different motifs among groups. And this has been shown to produce more realistic networks, maybe synthetic networks that can be synthetically generated. Temporal motifs capture interesting events on temporal graphs. So for example, one can use temporal motifs to identify some sort of activities that are frequent or occur in a short burst. And then there are some more nuanced applications, for example, considering cryptocurrencies network, or to analyze travel patterns on road networks and to understand how people commute from a place to another. And again, to enrich machine learning models and more. So given their wide applicability, in the last years, there has been a lot of research, and here I'm just like listing just a few papers, to have exact and approximate algorithms for temporal motifs. Now, unfortunately, temporal motif counts may not provide a complete view of temporal graph data. So we started from this observation because, of course, if you look only at the temporal motif count, you may not distinguish, for example, bursty events or that occur in a short period of time versus maybe events which are more persistent. And although this problem has been looked in some sense in the literature, still it's an open problem even nowadays. And in addition, temporal motifs don't really provide an information of where these counts that we see as a number occur within the network. So following existing literature for the densest subgraph problem, we propose a new problem, which is as follows. Given a temporal graph, a temporal motif, and a parameter delta, and remember these are all the parameters of the temporal motif counting that we had before. In addition, we require a weighting function tau over the set of delta instances. So the idea here is that tau is going to weight each delta instance according to some importance that we want to assign to each instance. So for example, if we assign an importance of 1 to each delta instance, then we are going to have simply the count of the delta instances in the set. Then what we want to find is the subset of vertices of the given temporal graph, maximizing a notion of density, where the density is with respect to the number of, let's say the number if tau is just a constant equal 1, for example, or let's say a different weighting schema for the delta instances in the given subnetwork. So ideally, we want to find the subnetwork where the density of temporal motifs is high. So our objective is the following. There are some nice properties about this objective. In particular, it captures important subnetworks, realizing many occurrences of a temporal motif. It's nice because the user can select flexibly, of course, like the temporal motif, and the weights assigned to each occurrence within subnetwork. So for example, we may try to assign a greater weight to instances which are more compact or more spread over the time duration delta. And of course, the user can pick the duration delta. So this has possible applications, of course, for temporal community detection, but also for advertisement and all the previous applications that I showed you before. Nice. Now that I convinced you that the problem is somehow interesting, how do we solve the problem? Well, first, let's look at the challenges. So we have that evaluating the objective function that we defined, in particular this function tau, since it's based on the number of delta instances inside the given subnetwork, it can be hard to compute. In particular, in general, the time is exponential because we need to enumerate all the occurrences of the motif inside the given subnetwork. And even with state-of-the-art exact algorithm, this may take up to exponential time in general. Then, since this is like our problem formulation is related to the definition of density for the standard density subgraph, you may know about flow-based algorithms or ELP formulations, but we want to avoid such procedures since they are very expensive. Usually they don't scale on very large data, and here we are concerned also with real temporal graphs. Okay, great. Let me introduce just one definition. In particular, we say that a temporal motif degree of a node V is the number of temporal motif occurrences, or delta instances, of a motif in which V occurs. So this means that these are all the delta instances in which V takes part in some edge over an instance. And this is the notation that I'm going to use. Okay, so our idea to solve this problem was the following: to rely on greedy peeling approaches, which are usually designed for the density subgraph problem. But the idea is to improve their scalability to randomized approximation. So this step is going to be clear immediately. Now, the basic structure of our algorithms, in particular, we designed two algorithms that difference for the way we combine the structure that I'm going to show you. I'm not going to go into details, but I'm going to present you the overall structure. Are as follows. So for each vertex V, instead of using the notion of temporal motif degree, we compute a 1 plus epsilon approximation of this temporal motif degree. Then we set this the set of vertices V1 to the set of vertices V. And then we start reducing the size of the graph, so peeling nodes from the graph, by looking at batches of nodes that have small degree controlled by a parameter Xi. So we're going to identify a batch of nodes, V prime, and then we're going to remove this batch of nodes, updating our new graph. And if the graph is very small, then we're going to output our greedy choice, which is the maximum density subgraph that we saw so far, but not according to its actual density. Remember, this is expensive to compute, but according to an estimate. Instead, if the graph is still large, then we are going to estimate the new temporal motif degree on the remaining graph. Remember, we updated the graph by removing a batch of nodes, and we're going to proceed, we're going to iterate this procedure. Okay, great. This is the algorithm. It's very simple. And the idea is that to compute the 1 plus epsilon approximation of the temporal motif degree, we can use any state-of-the-art randomized sampling approach for local motif approximation, which means that it computes this temporal motif degree for all the nodes in the graph. Great. So we're able to prove some guarantees about our algorithm. In particular, that our algorithm yields a solution, W, for some, which is equal VI for some I, of course, such that with probability at least 1 minus eta, the following holds. Basically, the density of the solution that we obtain is at least 1 over k, where this 1 over k comes from the greedy peeling approach, plus the fact that we are using k node motif. So every time we're looking at temporal motifs with k nodes. And this comes from the analogy of the static densest case, densest subgraph defined on the subgraph patterns. And this factor is tight, actually. Then we have 1 over 1 plus c, which comes from the batch peeling. So the fact that we're removing nodes in batches controlled by this parameter c. So we may lose some good quality solutions since we're removing more nodes at a time. And then a factor which depends on epsilon, since we're relying on estimates of both the temporal motif degrees of all the nodes and an estimate of the actual value of the objective function. And of course, this gives the approximation ratio. Now, we designed 2 different algorithms. They almost retain the same approximation ratio, and their time complexity, I'm not going to go into details, but it depends on the subroutine that we use to process the various samples to obtain the approximations, and some other like technical details. Okay, great. We did some experiments with our approaches. And in particular, we processed some medium and some large data sets, plus we did a case study on a Venmo graph, for which we have the information about some extra information about the edges that I'm going to describe later. So first of all, let me discuss efficiency. In particular, we tested different motifs, these 10 motifs that you can see here. So we had 3 different baseline algorithms. One is exact, one is batch, and one is greedy. And then we have our 2 different algorithms. What I'm going to show you now is on the x-axis, you're going to see like the temporal motifs. On the left plot, you're going to see the approximation ratio with respect to the optimal solution identified by the best algorithm that we were able to run on the specific instance. While on the plot on the right, you're going to see the average runtime of the various algorithms. So what we see is the following. So basically, for some instances, our 2 algorithms are the only ones that are able to actually conclude their execution, while all the baselines fail to process such large dataset. I didn't specify you the details, but the Bitcoin graph has 48 million nodes and more than 100 million temporal edges. So what we see is that for the runtime, our procedures are always the most efficient ones. And for the approximation quality, they often match the baselines, or sometimes they improve in very few cases. So finally, we also did some experiments to see what we obtain by setting some parameters and looking at the data. In particular, from the Venmo platform, we have that each edge is a transition. It's like an exchange of money between two users, which means that user U gives some money to user V at time t. And for each edge, we also have the attached message for which says, oh, I'm giving you money for this reason. So by setting the temporal motif with as a star-shaped motif and a small delta, we're able to identify this sort of bursty event, which is actually related to a particular event. So the central node is a merchant that got many bookings for a particular event. So the event was overbooked, and all of these edges that go out from the merchant, they correspond to the refunding to all these people that tried to book for the event, but of course the event was overbooked. Okay, so let me wrap up. In particular, in our work, we introduced a novel problem for the temporal motif densest subnetwork problem. We developed two different algorithms. The idea is to combine greedy peeling, which is always efficient, with randomized approximation of the temporal motif degrees. And we empirically show that our algorithms actually scale on very large data. There are various open challenges. In particular, from the theoretical point of view, we don't really control for the temporal evolution of the solution. So in particular, we don't have a direct control on how the solution spreads over the time. So for example, if it's bursty or persistent. So I think this is a nice direction for future work. And in addition, a nice thing would be to control also for the number of temporal motif occurrences inside the optimal solution. So one idea could be, for example, to obtain the smallest possible subnetwork, which contains a large fraction of the temporal motif occurrences of the entire graph. This would mean that this is like the most important subnetwork with respect to all the temporal motif counts that we observe on our data. Okay, thank you for your attention, and of course, I'm open to questions, and feel free to reach me if you want to discuss more.
Thank you, Ilie. Do we have any questions? Yes.
So you showed a few motifs that you run your algorithms on. Did you happen to run some motif where your algorithm wasn't running well on, like it wasn't terminating or something?
Yeah, we have actually, I think even on the plot that I showed you before, we have some instances for which the motif, we cannot process, for example, the motif. But this is mostly related to the underlying algorithms that we use to process let's say the graph, because it is still based on some enumeration on some samples that we obtain from the graph. But if the samples are not, let's say, sparse enough, processing them is going to require a lot of time. So actually, in these experiments, we set the maximum runtime to be at most 3 hours, which means that the algorithm didn't finish within 3 hours.
Cool.
Okay. And I guess another question.
This might be something. Why are they called al dente?
Well, the al dente is like a joke because actually I did my PhD in Italy, so.
Okay.
Pasta.
I see.
Yes, another question.
You said something about the anti-magnis on general temporal graphs. Is there something known for if you restrict the class of temporal graphs, let's say the underlying graph is planar?
Sorry, can you repeat the question? I didn't hear it so much.
Can you maybe come closer?
Yeah, sure. Should I just talk? Can you hear me now?
Yeah, thank you.
Yeah. So the NP hardness in the general case, is there something known if you restrict the temporal graph to planar graphs, underlying planar graphs, or any other restriction?
So the NP hardness is just the actual result goes as follows. Of course, this is related to the subgraph isomorphism problem, so you can prove that, of course, the problem is NP-hard. But the interesting result is that there are classes of subgraphs which can be counted in polynomial time on static graphs, but they are NP-hard to identify on temporal graphs.
Okay, thank you.
Welcome.